This is our GATE 4.5 presentation for our Distributed Energy Resource Optimization project. We are Group 8 and our client is Eaton. So our introduction, this project focuses on optimizing distributed energy resources, or DERs. The goal is to develop an algorithm that takes user-defined variables and optimization objectives to evaluate different system configurations. It will then compare these configurations against predefined system requirements to determine the most efficient DER setup. Ultimately, this will ensure the final system aligns with Eaton's specific outputs and objectives. My name is Francesca DeVito. I am the project schedule manager, and we have a couple other guys on here as
well. I'm Zach Rangel. I'm the assistant project manager.
Ferdinand Robb. I'm the secretary.
And I am Malachi Crane. I am the project manager.
Next, we have our project description. This slide will outline the problem that we're addressing. Eaton operates in a power management across various industries worldwide. The challenge comes from outdated central energy models that struggle to keep up with rising electricity demand. To address this, there is a critical need for sustainable energy infrastructure that not only meets future energy demands, but also minimizes the environmental impact. Ultimately, the beneficiaries of these solutions are both industries and consumers who will gain improved access to reliable and efficient energy.
This is our scope of work and method. Our location is Dubai in the United Emirates. Our research and initial design. Then we move on to our conceptual concepts and design development. Then our finalized optimization interface. And we scope down our methods by programming inside Python. We decided for our algorithm, we'll go with a mixed integer linear programming for our solutions, and we found the Gurobi API to be the most helpful and most useful. We decided to program this inside VS Code and inside a GitHub repository for easy access and easy teamwork and editing for pushing and pulling. We decided to utilize National Renewable Energy Laboratory, also known as NREL API, to pull wind sources and solar sources and battery sources, and we use tkinter to program our GUI.
For state-of-the-art, we took inspiration from Reopt, which is a software made by NREL. Reopt has a lot of things in common with our project. They share a lot of common objectives, such as economic viability of DERs, as well as sustainability. We used Reopt because it's a already more established energy optimization program. And we chose to model our input section similar to the way Reopt did it for theirs. As you can see in Figure 1, our PV inputs are nearly identical to the PV inputs used in Reopt. We also did this for the 3 other DERs that we have.
All right, so for our system solution, we broke down our program into 4 different subsections. Our first subsection is going to be our user interface, where there are 4 split up boxes for the user to enter their site-specific data. So the first one's going to be location with your city, state, and country, your load data, which is the average load data for each month, and the grid cost of energy. Our 4 weighted objectives, which are efficiency, cost, renewable impact, and power quality. And then our DER configuration specifications. So you have your PV, your wind turbine, your batteries, and your inverter specifications. Next, the API data pool is going to take this user-specific data and first gather the latitude and longitude based off the city, state, and country. Then we're going to use PV Watts, the version 8, which is an NREL solar data and PV output API that uses the location coordinates and user PV specifications to gather the AC power output at the specific site. And finally, we're going to use the NREL wind data API, which gathers the wind speed at a specified hub height from the user data at those designated coordinates. Next, we're going to send that data to our mixed integer linear programming optimization algorithm, which uses a software called Gurobi. Basically what this does is it's going to go through every single hour of every single year using our combined AC power outputs. It's going to come up with various configurations, the optimal configuration, how many wind turbines, how many PV panels. There's going to be multiple different DER components to choose from. It's going to figure out which one's the best based off the weighted objectives. And ultimately, it's going to output the total AC power generated, the breakdown between grid and the DERs, and a bunch of other data specifications based on these weighted objectives. Finally, we're going to visualize all of this in a user output that is similar to the user interface using a GUI with Tinker. This is going to show you the number of components, the total cost, and the objective-based data, as shown in the previous optimization program. Finally, we're going to add some graphs and visuals to this to show you kind of the breakdown, how many wind turbines, what the wind power output is, what the PV power output is, what the grid power output is for each different month. So now I'm going to show you our GUI that we have right now. So as you can see, it shows your location, your load demand, your weighted objectives, your DER resources. Basically, all of these are already filled out. I'm going to press calculate, and then it's going to, right now, it just shows you your calculation results. Eventually, it's going to show you the DER output. We're really close to finishing that up, but right now, we've just been working on our optimization algorithm. I'll show you what that outputted in the next slide. Results slide. You can see that we have our PV watts API data over here all the way on the left. This is automatically calculating using a bunch of different factors from PV watts. There's a bunch of other outputs that it calculates, but most of them we don't really need to use. This incorporates the inverter data as well to show you the overall efficiency of the system. Next, we have our wind turbine power output data. This is manipulated data that we have in our Python program, where it's basically taking that wind speed and using the hub height, the radius of the wind turbine, which are all user specified data, and it's showing you the power output. As you can see, it's all 1500 right here because it's a 1500 kilowatt wind turbine, and for each hour where the wind speed makes it so the power output exceeds that, so obviously you can't go higher than the capacity, but there are moments in time where that dips below 1500. Finally, our optimized output data shows that for each hour, it gives you our AC output for our solar, wind, and our calculated grid, which is basically just the remainder of that to cover the load. It's going to show you the total cost of the system. Then as you can see in here, we have 3 different turbines and 3 different PVs, and it's going to specify which ones are going to work the best, breaking it down into different quantities. We can set maximums and minimums for those quantities. It's all based on the user input. I believe that's all we have. Thank you so much for watching our presentation. I'm looking forward to finishing it up and showing you the final product.